Welcome back to the deep dive. This is
Right.
where we really try to accelerate your knowledge, taking years of engineering experience and distilling it right down.
Exactly. And today, we're tackling a big one. System design at massive scale.
It's a masterclass, really. Our goal is that knowledge acceleration, focusing squarely on how the biggest systems get built.
That's it. Because, look, you don't master this stuff from just one textbook. It really takes soaking up, years of collective wisdom from the industry giants.
Right. And the shortcut, which is what we're doing today based on our sources, is diving straight into the real-world architectural blueprints. How they actually did it.
We're skipping the pure theory and going right to the source, the papers, the engineering blogs that detail how places like Facebook, Amazon, Google, Twitter, Netflix,
The big names.
the big names, yeah, how they built systems handling billions of users, systems that just cannot go down, managing just unbelievable amounts of data in real time.
So we've got two main goals here for you listening. First, we want to pull out those core design principles, the shared ideas, like, say, eventual consistency or separating concerns that you see pop up again and again, regardless of the specific company.
Right, the underlying patterns. And
Second, we need to get into the specific technologies they built, the bespoke stuff like TAO or Dynamo or Bigtable or differential synchronization.
the famous ones.
Exactly. And not just what they are, but crucially, understanding the huge specific problem each one was invented to solve. Why did they need to build that thing?
That why is so important.
It really is. And for you listening in, this is honestly the fastest way to build that kind of architectural intuition that usually takes, well, frankly, a decade out in the field.
Yeah, it's a massive head start.
We're here to break down those, let's be honest, sometimes dense technical concepts, things like denormalization in a graph or, how Google Docs keeps everyone in sync when editing.
Getting at those aha
Yeah,
moment.
exactly. Those satisfying moments. Because getting this stuff, really absorbing it, it instantly levels up how you understand modern distributed systems.
Okay, so we've dug through a whole load of source material covering these key designs. Where should we start?
Let's start with maybe the biggest challenge of all, the social graph. Let's dive into the Facebook ecosystem.
Right. Facebook. When you say Facebook, you immediately think social graph. That's the core.
And it's not just the sheer number of users, billions of them. It's the connections, isn't it? The friendships, the likes, comments, shares.
It's the relationships between all those billions of users and data points, that dense, tangled web.
And the system has to navigate that web instantly, right? When you log in, it has to figure out your feed, your notifications, everything.
That density is the absolute key constraint. The social graph isn't like a simple table. It's this incredibly complex network. Objects, users, photos, events, all linked by associations, liking, tagging, friendship.
So loading your homepage means traversing huge chunks of this graph.
Instantly.
Yeah.
To assemble your context. And that needs speed and efficiency way beyond what, a traditional relational database could ever offer.
Which brings us neatly to a really critical architectural choice they had to make, specifically for handling historical data, like the timeline.
Yes, the timeline.
The source material mentions this explicitly. Facebook timeline, brought to you by the power of denormalization. And it talks about the challenge of building timeline, scaling up to hold your life story.
Denormalization. It sounds counterintuitive, right?
Totally. Normally, you avoid redundancy in databases like the plague because it causes consistency headaches. So why was it absolutely essential here?
Well, think about what the timeline actually is. It's an aggregation. It's not just one piece of data.
Right. It's posts, comments on those posts, likes from friends on those comments, maybe photos you were tagged in, events.
Exactly. All dynamically pulled together.
Yeah.
Now, imagine trying to build that on the fly from a perfectly normalized relational database.
You'd be doing hundreds, maybe thousands of complex SQL joins across loads of tables.
Yeah.
Every single time someone loads their timeline.
Correct. And doing that simultaneously for billions of active users, your database would just melt. Latency would go through the roof.
Okay, so the trade-off.
The trade-off was accept data redundancy to gain read speed. Denormalization here meant pre-calculating or, duplicating the relevant data bits into a single optimized structure, like a special row or object holding that aggregated view.
So when you load your timeline.
It's just one quick read operation, not this complex assembly dance every time.
Got it. So you sacrifice some simplicity on the right side, and maybe consistency is a bit harder to manage.
It definitely adds complexity there.
But you get this massive improvement in read latency for a very common operation. The architectural win was huge.
Absolutely worth the added complexity on the right path and consistency management.
Okay, so that's the timeline structure. What about the core data store, the thing actually holding the graph itself? The material points to TAO, Facebook's distributed data store for the social graph.
Right, TAO.
What makes TAO different from, say, just a standard NoSQL database?
TAO stands for the Associations and Objects System, and was purpose-built, really laser-focused on modeling and querying that social graph super efficiently.
Okay.
But its real genius, I think, isn't just the storage layer itself. It's the incredibly sophisticated caching layer built right into it, right on top.
Ah, so caching is fundamental to TAO.
It mandates it.
Mm-hmm.
TAO essentially requires this massive multi-level geographically distributed cache sitting right in front of the persistent storage.
So TAO isn't just a database then. It's more like a read-optimized service layer with caching baked in.
Precisely. It's designed from the ground up to handle an absolutely enormous read load at incredibly low latency. Because most requests, we're talking upwards of 99%, hit the cache.
Wow, 99%.
Yeah. The actual persistent storage layer mostly just deals with the writes, which are fewer, and those rare cache misses.
And why does that work so well for the social graph?
Because a lot of the graph structure is relatively static, right? You friend someone once, you maybe delete a post occasionally, but mostly those connections and objects stick around.
So you can cache them aggressively.
Exactly. Cache those objects, cache those associations, and that makes traversing the graph, figuring out who liked what, almost instantaneous. That caching strategy is fundamentally what makes the social graph usable at Facebook's scale.
And speaking of caching, the material specifically calls out scaling memcache at Facebook. I mean, the scale of their caching infrastructure must just be immense.
Oh, it's legendary. They didn't just have a few cache servers here and there. They architected it as this massive, unified cache pool. Thousands of machines spanning multiple data centers, all acting as one giant cache.
That must create its own challenges, managing something that big.
Huge challenges. They needed really specialized logic, just for cache consistency and invalidation. Think about it. You change your profile picture. That change has to ripple out and invalidate the old cached copies everywhere, globally, almost instantly.
Right. Otherwise, people see the old picture.
Exactly. So caching at that scale becomes its own massive architectural undertaking. It requires dedicated infrastructure, dedicated teams, just to manage the cache itself.
Okay, let's shift to specialized data. Media, photos, videos. That user-generated content presents totally unique problems, doesn't it? Facebook deals with billions, probably trillions of photos now.
Trillions, easily.
So how did they solve the problem described in Finding a Needle in Haystack, Facebook's photo storage?
Photos are tricky. They're big binary blobs. They're immutable, once uploaded mostly. The core problem they identified wasn't just storing the photo data itself. Disk space is relatively cheap.
It was the metadata.
Exactly. The data about the data. File names, permissions, crucially, the pointers to where the actual photo data is stored on disk. Managing the index for trillions of tiny files is incredibly expensive and slow for traditional file systems.
The lookup becomes the bottleneck.
Precisely. So Haystack's cleverness was in minimizing that metadata overhead.
How?
They designed Haystack to basically concatenate millions of photos and needles together into these huge multi-gigabyte, even terabyte-sized blob files, the Haystacks.
Okay, like one giant file containing lots of individual photos.
Right. By doing that, they dramatically reduced the number of distinct file entries the underlying file system needed to track. Millions of photos might only require managing the metadata for one large blob file.
And how do you find a specific photo then?
Retrieval just needs two pieces of information: which giant haystack blob the photo is in, and the specific byte offset within that blob where the photo starts, plus its length.
Ah, so no complex directory lookups, just point to the big file and jump to the offset.
Exactly. Simple calculation, one big read. It eliminated tons of expensive disk seeks and made photo retrieval incredibly fast. It's a great example of how sometimes the simplest storage model scales best.
And sticking with specialized systems, let's talk communication, real-time chat. That's a completely different beast, architecturally.
Totally different requirements.
Which is why the sources mention Erlang at Facebook chat, and the specific chat architecture.
Yeah, this is a classic example of polyglot persistence and, well, polyglot programming, using the absolute best tool for the specific job.
And Erlang was the tool for chat. Why?
Erlang's superpower is handling massive concurrency, millions of simultaneous connections, and fault tolerance. That's what it was designed for, originally in telecom systems.
Okay, so millions of people chatting at once.
Exactly. In a chat system, you need to maintain potentially millions of persistent active network connections. And if one server handling a bunch of those connections crashes,
You can't just drop all those conversations.
no way. The connections need to be seamlessly handed off to another server without losing messages. Erlang's design, with its lightweight processes, message passing, and built-in supervision trees, makes building that kind of resilient high-concurrency system much more manageable.
So it manages state and connection resilience better than, say, Python or Java might.
For this specific use case, absolutely. It allowed the Facebook chat architecture to handle those persisting connections and the low-latency message delivery really efficiently. It's built for what they call soft, real-time systems, ensuring things stay available even when parts fail. Perfect fit for global chat.
And finally, just looking broadly at feed efficiency, the sources highlight the need for constant iteration with things like serving Facebook multi-feed, efficiency, performance gains through redesign.
Yeah, that's maybe the biggest takeaway for anyone learning this stuff.
That these systems are never done.
Never. That paper is great because it shows how even seemingly small tweaks in how feeds are aggregated or where caching happens, maybe moving a calculation slightly closer to the user's edge location, can result in huge performance wins when you multiply that saving by 1 billion users.
So redesigns aren't failures, they're necessary evolution.
Absolutely necessary, especially when you're constantly balancing the complexity of delivering highly personalized content against the absolute need for speed and efficiency. It's a living architecture.
Okay, let's shift gears. We've talked about the dense social graph at Facebook. Now let's move to systems where maybe the top priority is slightly different. High availability for e-commerce and massive scale for media streaming.
Right. We're moving from systems obsessed with immediate social connection to systems where resilience, uptime, and deep user engagement are paramount. Think Amazon and Netflix.
With Amazon especially, fault tolerance isn't just nice to have, it's everything, right? If the site goes down during a major sales event, it's catastrophic. Lost revenue, damaged reputation. So their architecture fundamentally prioritizes availability, which leads us directly to maybe the most influential paper to come out of Amazon.
Has to be Dynamo, Amazon's highly available key value store.
That's the one. Foundational reading. Seriously, if you're designing distributed systems, you have to understand Dynamo.
Why was it created? What problem did it solve that existing databases couldn't?
It really came from operational pain. In the early days, Amazon, like many others, relied on traditional relational databases. But they found these databases just couldn't handle the scale, and crucially, single points of failure in the database layer could bring down huge parts of the shopping experience.
Like the shopping cart.
Exactly. Core services like the shopping cart, session management, things that had to work. Amazon decided that for these critical services, they valued availability and partition tolerance more than they valued strong, immediate consistency. That was the key philosophical shift.
Okay, let's unpack highly available in this context. What does it really mean for Amazon? It means the system must be able to accept reads and writes, basically 204/7, even if parts of the network are down or servers fail. No single failure should prevent a user from, say, adding an item to their cart.
And how does Dynamo achieve that? What's the architectural pattern?
It uses a combination of techniques, but fundamentally it's about decentralization and aggressive replication. Data isn't owned by a single master node. It's replicated across multiple nodes, often spread across different physical locations or availability zones.
How does it know where to put the data and find it again?
Techniques like consistent hashing are used to map a piece of data, like a user's shopping cart, identified by a key, to a set of nodes responsible for storing it. And importantly, there isn't one central coordinator managing everything.
Okay, but if data is replicated and you can write to different copies during a network split, how do you deal with conflicting writes? Doesn't that break consistency?
That's the core trade-off. Dynamo embraces eventual consistency. It guarantees that eventually all replicas will converge to the same state, but it allows for temporary divergence during failures.
How does it manage that divergence and eventual convergence?
Often using techniques like vector clocks. Think of it as a way for the system to track the history or causality of different writes, even if they happen concurrently on different replicas. When the network partition heals, or the nodes can talk again, they can compare these vector clocks.
And figure out which write happened after another, or if they are true conflicts.
Exactly. The system then has a reconciliation policy. Maybe it keeps both conflicting versions and asks the application layer to resolve it later, or maybe it uses a simple rule like last right wins. The point is, it prioritizes accepting the right now over ensuring immediate consistency everywhere.
So for the shopping cart example, it's better to let a user add an item, even if the cart total might be slightly off for a moment due to a network issue, than to show them an error page.
Precisely. Better a potentially slightly stale view than denying service, especially during peak times. That willingness to trade strong consistency for near-perfect uptime was revolutionary, and the simple, scalable key-value store model enabled it. That's why Dynamo's design ideas are now everywhere in NoSQL databases.
Makes sense. Okay, let's pivot. Netflix. Another giant, but with totally different challenges, streaming massive video files globally.
Yeah, the constraints are different. The source, a 360-degree view of the entire Netflix stack, really highlights the sheer breadth.
It's not just hitting play on a video file, is it?
Oh, not even close. The Netflix stack is huge. It starts with content injection, taking a master movie file and transcoding it into hundreds of different formats and byte rates.
Why so many versions?
To optimize for every possible device, phone, tablet, smart TV, old laptop, and every possible network condition, blazing fast fiber or spotty 3G. Then there's managing their massive cloud infrastructure, mostly on AWS.
They're famously huge AWS users.
Absolutely. Then there's their own content delivery network, Open Connect, getting those video files cached close to users worldwide. Plus, the entire user interface, search, billing, device management. It's incredibly complex.
And handling billions of user connections, delivering petabytes of data constantly.
It's a beast. But what's really interesting about the Netflix architecture, highlighted in the sources, is how it's built for learning.
You mean A/B testing? The source, it's all about testing. The Netflix experimentation platform talks about this.
Yes, but it's more fundamental than just running marketing tests. For Netflix, experimentation is a core architectural feature. Their entire platform is designed to allow engineers to easily route different segments of users down different code paths or different infrastructure configurations.
So they can test changes live?
Constantly. They test everything. Different compression algorithms, new UI layouts, different recommendation models, even tweaks to load balancing strategies. All running live in parallel with careful measurement without disrupting the main user experience.
So the architecture itself has to support that user segmentation, traffic routing, and data collection for the experiments natively.
Exactly. The experimentation platform itself is a sophisticated distributed system. It has to ensure tests are statistically sound, results are captured reliably, and they can roll out successful changes quickly. It's baked into their engineering culture and their infrastructure.
And that constant testing is what lets them optimize relentlessly for user engagement, right? Which brings us to recommendations.
The heart of the Netflix experience.
The sources give us a two-parter. Netflix recommendations, Beyond the 5 Stars Part 1 and Part 2. How did their thinking and their architecture evolve here?
Well, the big realization detailed in those pieces was that simple 5-star ratings, the explicit feedback, just weren't cutting it.
Why not? Seems straightforward.
People rate things aspirationally sometimes, differently from how they actually watch. And frankly, most people just don't rate stuff very often or very consistently. So the signal is noisy and sparse.
So they shifted focus.
They shifted from trying to predict your rating to predicting your behavior and satisfaction. What will you actually watch? What will keep you engaged with the service? It became about analyzing implicit signals.
Implicit signals? Like what?
Not just what you watched, but when you watched it. How long you watched. Did you binge watch a series? What device were you on? Did you pause, rewind, abandon a show halfway through? Even analyzing the patterns within a genre you watch. Extremely granular behavioral data.
Wow. So architecturally, what did that shift require?
It required building massive, sophisticated machine learning pipelines. Those papers detail their move towards complex hybrid models combining collaborative filtering, people like you also liked, with content-based filtering. You like this action movie, here's another similar one.
And processing all that granular behavioral data you mentioned.
Right. The architecture had to scale up to ingest and process these huge high-velocity streams of user interaction data, not just simple user item rating matrices. They needed systems for feature engineering, training complex models, and serving recommendations with low latency.
So the recommendation engine isn't static, it's constantly learning and updating.
Constantly. It's serving up dozens of personalized rows on your screen, each potentially driven by a different model or algorithm, all being A/B tested. The architecture is geared towards low latency model inference and rapid deployment of new models, all feeding back into that core goal. driving viewing hours and user satisfaction. It's like an architectural engine for applied psychology.
Okay, let's move to Google. If Facebook mastered the social graph and Amazon mastered resilience, you could argue Google really engineered the fundamental building blocks for modern cloud-scale data infrastructure.
I think that's fair. Many of the concepts underpinning cloud computing today originated or were scaled massively at Google first. And we have to start with a truly foundational paper, the Google File System, Google Docs.
GFS, you hear about it all the time.
Mhm.
What was the core problem it solved?
It tackled the challenge of storing absolutely massive data sets, think petabytes, reliably across thousands of unreliable commodity computers. Remember, back then, high-end reliable storage was incredibly expensive. Google wanted to build its infrastructure on cheap, standard hardware that was expected to fail regularly.
So fault tolerance on cheap hardware was key. How did GFS achieve that?
Architecturally, it did a few key things. It broke files into large, fixed-size chunks, typically 64 megabytes, much larger than typical file system blocks.
Why large chunks?
It reduced the amount of metadata the system needed to manage. Fewer, larger chunks are easier to track than billions of tiny ones. These chunks were then replicated, typically 3 times, across different machines, chunk servers.
So if one machine died, the data was still safe on others.
Exactly. The other key part was its simplified design. It was optimized for Google's main workloads back then. Huge sequential reads and, importantly, append-heavy writes. Think web crawls, log processing. It wasn't great for random writes like a traditional database file system.
And how was it all managed?
There was a single master server responsible for keeping track of all the metadata, which chunks belonged to which file, where the replicas of each chunk were located. That single master was a potential bottleneck, but it massively simplified the overall design and consistency model. GFS basically made petabyte-scale storage on commodity hardware feasible.
Okay, so GFS is the underlying layer, handling the raw file storage reliably. But Google obviously needed to work with structured data, not just giant files. That leads us to Bigtable, a distributed storage system for structured data.
Right. GFS is the foundation. Bigtable is the house built on top.
So how is Bigtable different? It's not just a file system.
Now, Bigtable is a database. Specifically, it's described as a distributed, persistent, multi-dimensional, sparse map.
Okay, let's break that down. Sparse map.
Think of a giant table with potentially billions or trillions of rows and potentially millions of columns. But most cells are empty, sparse. Each cell is indexed by a row key, a column key, and a timestamp. This structure is incredibly flexible and perfect for storing things like web index data, user profiles, structured logs data that has structure but doesn't fit neatly into a rigid relational schema.
And it runs on top of GFS.
Yes, Bigtable uses GFS for its persistent storage. So it inherits GFS's reliability and scalability for handling the underlying data chunks, which in Bigtable's case are called tablets. But Bigtable adds the crucial data model, indexing, and API for efficiently querying and managing massive amounts of structured data.
So GFS handles the bytes. Bigtable organizes those bytes into rows, columns, and timestamps, making it searchable and useful.
That's a great way to put it. GFS provides the durable storage. Bigtable provides the structured data management system on top. It was designed specifically for Google's scale needs.
Makes sense. Now, sticking with Google, perhaps one of the most fascinating pieces of architecture, especially for collaborative tools like Google Docs, is differential synchronization, Google Docs.
This is where things get really mind-bending. It's all about real-time collaboration.
The simultaneous editing problem, right? How do you keep multiple people typing in the same document perfectly in sync, even with network delays and potential conflicts?
Exactly. Imagine you and I are editing the same sentence thousands of miles apart. I hit delete on a word just as you start typing a new word right next to it. My delete command reaches your computer milliseconds after you've already typed half your word.
Chaos ensues. Documents diverge.
That's the risk. A naive approach might just overwrite changes, leading to data loss or garbled text. It seems like an impossible consistency problem given the asynchronous nature of the internet.
So how does differential synchronization solve it?
The core idea is elegant. Instead of constantly trying to send and sync the entire document state back and forth, which is inefficient and prone to race conditions, you only send the differences, the diffs or patches that describe the changes a user makes.
Okay, so I type hello. My client sends a patch like insert hello at position 5.
Sort of, yes. The client calculates a patch describing its change relative to its current version of the document. It sends this patch to the server. The server applies the patch to its master copy and acknowledges it.
But what about the conflict scenario? My delete patch and your insert patch arrive at the server around the same time.
That's the clever part. Differential synchronization, often implemented using algorithms like operational transformation, OT, includes logic to handle these conflicts intelligently. The server doesn't just blindly apply patches.
What does it do?
It uses the OT logic to potentially transform one patch based on the other conflicting patch before applying it. So, in our example, when your insert patch arrives, the server might realize my delete patch has already been applied. It transforms your patch to say, insert new word at the new position created by the deletion.
So it adjusts the patch to make sense in the context of other concurrent changes.
Exactly. It ensures that even with conflicting concurrent edits and network latency, both clients and the server eventually converge to the exact same document state without losing user intent. It's a mathematically complex but incredibly powerful way to achieve strong consistency in a highly distributed, real-time collaborative setting. Absolutely critical for things like Google Docs.
Okay, shifting gears slightly within Google Video. YouTube. Different scale, different type of data. We're looking at YouTube architecture and insights from the Seattle conference on scalability, YouTube scalability material.
YouTube scale is just staggering. The unique challenge isn't just storing video files, though there's a lot of that. It's the processing and delivery.
You mean transcoding?
Primarily, yes. When someone uploads a video, that single file isn't what users actually watch. YouTube has to transcode it, re-encode it into dozens of different formats, resolutions, 4K, 1080p, 720p, 480p, etc., and byte rates.
Why? Again, optimization.
Exactly. To ensure a smooth viewing experience on any device, any network connection, anywhere in the world. That transcoding process itself is a massive distributed computing job. You need huge clusters of machines just processing video 24/7.
So ingestion and processing is one major architectural pillar. What about delivery?
That's the other huge piece. Once you have all these different versions, you need to get them close to the users. That means a massive, highly optimized content delivery network, CDN. YouTube uses Google's global network to cache popular videos in locations all around the world.
So when I hit play in London on a popular video,
You're likely streaming it from a server physically located very close to you, maybe even within your ISP's network, not all the way from a central Google data center in the US. The architecture is heavily focused on optimizing that transcoding pipeline and the global CDN routing to minimize buffering and deliver video instantly. It's a specialized problem that goes way beyond just storing files.
okay, let's broaden out again. We've seen social graphs, e-commerce resilience, foundational data infra, and video. Now let's look at services really defined by immediacy, real-time feeds, unique identification, and just the sheer diversity of tech stacks.
Right. Platforms where speed of information dissemination is the core product. Twitter is the classic example here.
Their entire history feels like a battle against scale, doesn't it? Especially that high fan-out problem they talked about.
Absolutely. The sources mention the ambition of scaling Twitter, making Twitter 10,000% faster while handling 150 million active users. That fan-out issue is brutal. One celebrity with, say, 50 million followers tweets once.
And boom, that single write triggers potentially 50 million reads almost instantly as it needs to appear in all those followers' timelines.
Exactly. Early Twitter architectures really struggled with that load. Trying to compute everyone's timeline on demand, pulling data, just didn't scale efficiently.
So they shifted strategy. This seems related to the principles in timelines at scale.
It is. That paper and Twitter's evolution really encapsulates the architectural decision between push versus pull for feeds. For their specific needs and scale, Twitter largely moved towards a push model, sometimes called right-time fan-out, at least for most users. Meaning, when that celebrity tweets, the system immediately does the hard work of pushing or injecting that tweet into the pre-computed timeline data structures for each of their millions of followers.
So the work happens when the tweet is written.
Right. It's very intensive. On the right side, one tweet triggers potentially millions of writes into timeline caches or stores. But the huge advantage is that when a user reads their timeline,
It's super fast because it's already calculated and waiting.
exactly, the read operation becomes incredibly simple and low latency, which is essential for that immediate, real-time feel of the Twitter feed. It's another example of trading complexity, moving it from read time to write time to optimize for the core user experience.
Okay, but for any of this to work, timelines, tweets, user actions, every single piece of data needs a unique identifier, right? especially in a globally distributed system.
Absolutely critical.
Yeah.
You can't just use standard database auto-increment IDs. They don't work across multiple databases or data centers, and a single ID generator becomes a massive bottleneck and single point of failure.
Which is why Twitter developed that specialized service, announcing Snowflake.
Yes, Snowflake is such an elegant solution to this distributed ID generation problem. It's a network service designed purely to mint unique IDs at extremely high scale with simple guarantees.
How does it work? What makes a Snowflake ID unique and useful?
A Snowflake ID is typically a 64-bit integer composed of several parts, bit shifted together. Crucially, it includes a timestamp, usually milliseconds as a specific epoch, giving you approximate time ordering.
Okay, so IDs are roughly chronological.
Roughly, yes. Then it includes a machine ID or worker ID, uniquely identifying the specific Snowflake server instance that generated the ID. This ensures uniqueness even if multiple servers generate IDs in the same millisecond.
Prevents collisions between machines.
Exactly. And finally, there's a sequence number within that millisecond on that specific machine. If one server gets multiple requests in the exact same millisecond, the sequence number increments, ensuring each ID is still unique.
So timestamp plus machine ID plus sequence number is globally unique, roughly time-sortable ID.
Precisely. Generated decentrally, without coordination, at incredibly high rates. It's fundamental for tracking data, ensuring consistency, and enabling efficient lookups in their distributed databases. The fact they needed a dedicated service just for IDs really underscores the complexity of scale.
It really does. Okay, let's touch on some other platforms mentioned, highlighting the diversity. Instagram, for example.
Right, the source notes for Instagram, even early on. 14 million users, terabytes of photos, hundreds of instances, dozens of technologies.
What does that tell us architecturally?
It screams polyglot persistence and technological diversity. Their challenges were and are a mix. Massive photo storage and retrieval, like Facebook's Haystack, but perhaps with different access patterns and metadata needs, combined with managing a rapidly growing social graph.
And they famously use different tech for different parts, right?
Yeah, they were well known for scaling Postgres, a relational database, surprisingly far from their core data, but heavily relying on things like Redis, an in-memory key value store, for caching, feeds, and other specialized tasks, alongside their photo storage systems. It shows you use the best tool for the job.
No one-size-fits-all database.
Definitely not at that scale. You need relational databases for certain consistency guarantees, key value stores for caching and speed, maybe graph databases for complex relationships, specialized file systems for media.
Makes sense. How about a purely real-time system like Uber? How Uber scales their real-time market platform? What are the key demands there?
Uber is fundamentally about real-time matching based on location. The absolute critical architectural requirement is handling a constant, high-velocity stream of location updates from potentially millions of drivers and riders simultaneously.
Geospatial data is the core.
It is. And the system needs to index this rapidly changing geospatial data efficiently. They often use specialized libraries or techniques like Google's S2 library or Uber's own H3 library, which divide the world into hexagonal grids for efficient indexing and querying.
So when I open the app looking for a ride,
The system needs to perform an incredibly fast geospatial query. Find available drivers within X radius of this rider's current location. This usually hits a specialized real-time data store, maybe a distributed cache optimized for these kinds of spatial lookups.
the challenge is handling millions of location rights while serving millions of read queries for nearby drivers, all within fractions of a second.
That's the crux of it. Managing that concurrent write load while ensuring low-latency reads for the matching algorithm is the core scaling problem. It demands specialized indexing and data storage optimized for real-time geospatial operations.
Okay, one more visual one. Pinterest. Sources mention scaling Pinterest and the Pinterest architecture update. What's their unique angle?
Pinterest is all about visual discovery, so their scaling challenges revolve heavily around images and, crucially, recommendations based on visual similarity.
So less about social connections, more about the content of the images themselves.
Largely, yes. Architecturally, this means needing scalable image processing pipelines, ingesting billions of pins, analyzing them, optimizing them, and then the really hard part, applying sophisticated machine learning, often deep learning, to understand the content of those images and find visually similar pins for recommendations.
That sounds distinct from Facebook's graph or Amazon's retail focus.
It is. Their architecture updates often talk about moving to microservices to handle different parts of this pipeline and continuous work on improving their visual search and recommendation models. It's a specialized focus on image analysis, metadata extraction, and large-scale similarity search.
And the sources list others too, just briefly.
Yeah, quickly, LinkedIn,
Mm.
a brief history of scaling LinkedIn, focuses on the professional identity graph, search, and messaging in that context. Dropbox, how we've scaled Dropbox, is obsessed with file synchronization consistency across devices, a really hard problem involving block storage and sync logic.
Flick architecture for photos again, and WhatsApp.
Flickr, another photo pioneer.
Yeah.
And WhatsApp is fascinating. They famously achieved massive scale, hundreds of millions of users, with a very small engineering team, partly by choosing technologies like Erlang, known for efficiency and concurrency, and maintaining a very lean, focused architecture.
The common thread seems to be general purpose doesn't cut it. You need specialized systems.
That's the inescapable conclusion at this kind of scale. Purpose-built infrastructure, tailored to the specific problem, is the only way forward.
So we've covered these foundational architectures, the blueprints from the giants, but the source material makes another really crucial point, doesn't it?
It absolutely does. This kind of knowledge isn't static. You don't just learn about Dynamo once and you're done.
Right. The learning has to be continuous. And the sources point directly to where a lot of that current learning happens.
Exactly. We move from the historical papers, the blueprints, to the front line. The recommendation is crystal clear. Regularly reading the engineering blogs published by these companies is critical.
Why? What do you get from them?
You get invaluable current insights. How are they adapting these foundational principles today? What new challenges are they facing? What specific technologies are they adopting or migrating away from now? How do they solve a recent outage or scaling bottleneck? It's the real-world, up-to-date application of the theory.
And it's not just for general knowledge, is it? The source explicitly mentions interview preparation.
Yeah, it calls it a great idea. If you're interviewing at, say, Airbnb, knowing about their recent work on scaling their search infrastructure or challenges they've blogged about in their marketplace dynamics that shows you've done your homework. It demonstrates genuine interest and competence beyond just textbook answers.
So knowing the theory of Bigtable is good,
Foundational, yes.
but knowing how Google might be evolving its consistency models now, or how a different company like, say, Stripe is applying similar principles to financial data, that's the next level.
That's the practical, current knowledge that lives on these blogs. It connects the theory to what's actually happening in production today.
And the list provided in the sources shows the breadth. We're talking blogs from Airbnb, Amazon, Dropbox.
GitHub, talking about scaling Git itself. Expandle on analytics infrastructure. Slack on real-time messaging APIs. Stripe dealing with the insane complexity of global payments.
Then Thumbtack for local services, Yelp for reviews, Zoom for video conferencing, each facing unique scaling pressures.
And don't forget, aggregators like highscalability.com, which often summarizes and links to the best technical posts from across the industry. It's a great starting point.
So the takeaway is make reading these a habit.
Absolutely. The source says reading these regularly helps us become better engineers because it shifts your thinking. You start seeing patterns. You start asking yourself, okay, if I were building a new service, what would my equivalent of Snowflake need to be? What availability trade-offs, like Dynamo, would I make?
It moves you from just knowing the concepts to thinking about the practical, constrained, real-world decisions.
Precisely. It's about internalizing the why behind the choices these incredibly smart teams are making every day. Hashtag outro. So that was quite a journey. We've navigated through the architectural blueprints of some of the world's biggest tech companies.
We really tried to pull out those core lessons you need for thinking about system design at scale.
And we saw those two key mandates kept coming up, right? First, pay attention to the shared principles, things like highly available data stores, the critical role of caching, the need for unique ID generation. These patterns repeat.
And second, understanding the specific, often bespoke technologies created to solve massive problems. Denormalization for Facebook's timeline, differential synchronization for Google Docs, GFS and Bigtable for core data, Dynamo for availability, TAO for the social graph cache.
Understanding why they were built is key.
We also saw that getting this knowledge takes discipline. It's not easy stuff. But studying how these successful systems were built, how they evolved, how they were redesigned, that effort really pays off.
Yeah, the source emphasizes that the hard work will be paid off, and it equips you with the foundational concepts.
And critically, none of these systems started perfect, did they? Facebook, Twitter, Pinterest, they all went through major updates, sometimes painful redesigns, to meet the next level of scale.
It's an iterative journey, always evolving. Practice makes perfect, as they say, even in system architecture.
Which brings us to our final thought, something for you to maybe mull over. We talked a lot about specialized systems today. Dynamo, built for that high availability eventual consistency model. Bigtable, built for massive scale structured data indexing and querying.
Two powerful but different philosophies.
Right. So here's the question. If you were designing something new today, maybe a system we haven't even fully imagined yet, like a globally distributed, highly complex blockchain application, or a real-time global content moderation platform, how might you combine the core principles of Dynamo and Bigtable?
Ooh, interesting. Fusing them somehow.
Yeah. How could blending Dynamo's extreme availability and partition tolerance with Bigtable's power for structured, indexed data queries solve a future system design challenge? What kind of hybrid system could emerge from that?
Trade-offs would you make? What would the core strengths be? That's a really interesting thought exercise. Combining the best of both worlds, perhaps.
Perhaps. Something for you to think about as you apply these concepts we've dived into today.
Definitely food for thought.
Yeah.
Thanks for joining us on this deep dive.
We'll catch you next time.